Hello ladies and gentlemen. I realize that this is a somewhat outdated cartoon as Halloween was a good bit back, but I thought it was humorous nonetheless. So if you want to take a little time to read it, go ahead and pause the video, otherwise we go on. Today we look at 6.2, Antidifferentiation by Substitution. As we consider various rules and their importance for integration or antidifferentiation, there are a few rules that are used often as much as what we refer to as U substitution, and that's what we're going to look at today. U substitution is to antidifferentiation what chain rule was to differentiation, if you remember the chain rule from a few chapters back. We will first discuss some shortcuts for antiderivatives. We'll then do the U substitution for both indefinite and definite integrals. And we begin with just a little terminology. Just a reminder to you, the antiderivative, we often write like this, integral f of x dx. This is referred to as the indefinite integral. Indefinite integral. And the reason we say it's indefinite is it does produce, if you remember back in slope fields, the various graphs. You could have a certain shape, and that shape could be shifted up or down, left or right, just depending on the graph. So this is called the indefinite integral. These are the ones that have the plus c. We don't know what the c is. The c is called the constant of integration, and also I want to remind you that a capital F like this often does denote the antiderivative. Alright, just a little practice for you. Evaluate the following integral, the integral of x squared minus sine x dx. This requires us to know some antiderivatives. The antiderivative of x squared, x cubed over 3. We've done that one several times. The antiderivative of sine would be negative cosine, but that negative there makes it a plus, and then we put the plus c. Simple antiderivative rules. We do want to look at some properties and shortcuts of indefinite integrals. This first one we've talked about before. If you have a constant term on your function, you can bring that constant term out, such as this right here, and then just multiply it by the answer. We've also discussed this one before. If you're adding or subtracting, you can break it up into two separate integrals. This, ladies and gentlemen, is one of the first shortcut rules, though, that we see. I think I've mentioned this to both of my classes in the past. Nonetheless, here it is. If you have something to a power, now this is a variable to a power. This does not work if u is a number, like 2 to the x. So this would be something like x squared or x cubed. You raise the exponent power by 1, divide by the new exponent, plus c. U to the negative 1 or 1 over u, same thing. The integral is natural log. Makes sense. Antiderivative of 1 over u is natural log u. Note the absolute value bars. Those are very important, especially when it comes to doing definite integrals. You cannot take the natural log of a negative. That's why we throw those absolute value bars in. Some others that you probably already know from trig. The integral of cosine is sine. Secant squared is tangent. These are all antiderivatives. The antiderivative of secant tangent is secant, and so on. I would encourage you to keep this list handy. Lots and lots and lots of antiderivatives you're going to need to know as we go throughout this chapter and next. Alright, some more. Integral of e to the u is e to the u plus c. This is one here that came up in your 6.1 homework. The integral of a to the u, that would be something like 2 to the x, 5 to the x, etc., is a to the u over natural log a plus c. The integral of natural log u, this is actually one that will work out as a problem when we get to the next section when we do integration by parts, but for now it's a shortcut rule. The integral of natural log u is u natural log u minus u plus c. And the integral of log base u, or log base a of u, you see here, u natural log u minus u all over natural log a. Keep those formulas handy, they will be helpful. Now, when we are working antiderivatives, you've got to pay very careful attention to the differential. Now, this is funny because the differential is the part that most people will leave off in the problem. They'll leave off that little dx part on the end. But the dx is actually quite significant. Consider these three situations. The integral of f of x dx, the integral of f of u du, and the integral of f of u dx. Now, some people would say, oh, the u's and the x's don't make a difference here. It's all the same thing, but it's actually quite different. So let's look at the first one. The integral of f of x dx. I plug the x cubed plus 1 in for f of x, and now I antidifferentiate. This would be x to the 4th over 4. This would be x, and then we have our plus c. What about this one, though? The integral of f of u du. Well, first of all, I'm going to take the u and I'm going to plug it into f. So this will come in and plug in here. And then the du, here you see the x squared being plugged in. The du is the derivative of u. So the derivative of x squared is 2x dx. We simplify. That's x to the 6 plus 1. We can take and distribute our 2x. 2x to the 7th plus 2x, now we anti-differentiate. That would be 2 to the x, 2x to the 8th over 8, which would simplify. That would be x squared, and then plus c. Here we have f of u dx. I'll plug the u in, but then I'll just leave the dx as it is. So that's x to the 6 plus 1 dx. Anti-differentiate. X to the 7th over 7 plus x plus c. Now we come to u substitution. Again, ladies and gentlemen, when did we use chain rule when we were differentiating? We used chain rule whenever there was a composite function, something inside of something else. Well, when you are integrating and you have that same kind of a composite function, we will use what we call u substitution. And u substitution begins with the substitution. What will u replace? Well, u usually replaces something that's on the inside. So if I look at this, sine of x times e to the cosine x, I see that cosine x is inside of the e function. So I'm going to let u equal cosine x. I next take the derivative of that. The derivative, du, would be equal to negative sine x dx. Take the derivative using differentials. Now this is significant because what I see here, ladies and gentlemen, is I see this is u right here, and this sine x and this dx together almost make, and I do emphasize almost make, the du. What's missing? Well, the only thing that's missing is a negative. So I can put a negative on it, but to offset that, I need to put a negative out here. Two negatives would make a positive. And that's what I've done here. Now we make our substitutions. All of this right here becomes e to the u. This part right here, negative sine x dx, together make du. And now what we have is a much, much simpler problem. What's the integral of e to the u? Well, it's e to the u plus c. Don't forget the negative. And the final step of every good substitution problem is to resubstitute. Remember, u back at the beginning was cosine x. I'll plug that in right there. And there's my final answer. Let me adjust the screen so you can see it clearly. Alright, another u substitution problem. So again, we ask ourselves the question, what's on the inside? Well, very clearly, what's on the inside is 5 plus 2x cubed. So that's going to be our u value. What is du? Take the derivative. The derivative of 5 would be nothing, but of 2x cubed would be 6x squared dx. Now, if I look up here, this all right here would be u, square root, so square root of u, x squared dx. I've got x squared dx, but I need 6x squared dx, so I need a 6 here. Well, if I put a 6 here, no big deal. I'll come out here, I'll offset that with a 1/6. 1/6 and 6, both multiplication, would cancel out. Now, this becomes the square root of u. 6x squared dx becomes du. And now I can rewrite the radical u as u to the 1/2. Now, raise it by 1, u to the 1/2, increase the 1/2 by 1 is 3/2. Divide by that new number, 3/2. 3/2 and 1/6 can simplify. Let me adjust the screen again. To 1/9. If you take the 3/2 out and flip it, multiply by 1/6, you get 1/9. And now again, all that remains, resubstitute. Don't forget that resubstitution. It causes people points on tests every time. Alright. Using substitution again. Now, at first, this one does not look like a substitution. In fact, if you go back and look, we actually have a formula for this one, the integral of cotangent x. But we get that formula by doing u substitution. What I'll do first, though, is I'll rewrite cotangent as its quotient identity, cosine over sine. Now, what's on the inside? Well, this one's kind of hard to determine. In a fractional situation like this, I look to the denominator to be the inside. There are reasons for that, and you'll see that as you go throughout the chapters. So, what's on the bottom? On the bottom is sine x. That's going to be u. What's the derivative of u? Du is cosine x dx. Now, look at how perfect this is. On the bottom is our u. All this on top, cosine x dx is du. So 1 over u du. What's the integral of 1 over u? We had a formula for that a few minutes ago. It is natural log u, absolute value. Resubstitute. Now, the next thing we want to look at, using trigonometric identities to do substitution. There are various identities that we can do for. So on this first one, I have a cosine squared, and you may think, well, we've got some things for cosine, but not for cosine squared, plus it's on the bottom. Well, cosine squared's on the bottom, we'll flip it to the top, secant squared. Now I have an identity for the integral of secant squared is tangent. And you may ask, where does this 1/2 come from? Well, if I were doing u substitution, u would equal 2x. And then du would be 2 dx, so I would need a 2 in there. And if I put the 2 there, right there, I need the 1/2 to balance it out. Now the integral of secant squared is tangent. Notice the 1/2 is still there. Cotangent squared is cosecant squared 3x minus 1. Again, why do I do that? Well, I don't have an identity for cotangent squared, but I do have one for cosecant squared. I'll split this up first of all so that I can take the integral of my 1 and my cosecant squared separately. Now on this cosecant squared, I'll have to let u equals 3x, and just like up here we had to do a 2 and a 1/2, on this one I would have to do a 3 and a 1/3. That's what I've done right here. Now with the 1/3 and the 3 out of the way, what's the integral of cosecant squared? It's negative cotangent. So there's where we get this. The integral of 1 is x plus c. Cosine cubed, you look at it and say, well, I don't have any identities for cosine cubed, and that's true. But I can split this up to be cosine squared times cosine, and I do have an identity for cosine squared. That's 1 minus sine squared, Pythagorean identity. Now doing u substitution on this one, I would let u equal sine of x. U is sine of x, and if u is sine of x, let me go back, move the screen down. Sorry about that. If u is sine of x, then du would be cosine x dx, so that would take care of the cosine. The integral of 1 would be x, and then the integral of u squared would be u cubed over 3, and then I just plug the sine back in, plus c. If I've gone through these too quickly, please let me know tomorrow in class and we can slow down a little bit and go through them again. Alright, evaluating a definite integral by substitution. We're going to take the integral from 0 to pi over 3 of tangent of secant squared x dx. I'm sorry, that's supposed to be tangent x, secant squared x dx. It is obviously a typo. First of all, we'll let u equal tangent x. Now again, you say, why? There's nothing on the inside. Well, no, there's not anything on the inside. But I do know that secant squared is the derivative of tangent. So that being said, that's why I selected u, because when I take du, I've got my secant squared. That's all taken care of right there. So now this becomes the integral of u here and then du right there. Very simple. Now you may be wondering, where do I get these numbers? The 0 didn't change, but I got radical 3. Well, there are two philosophies on this. One is to, when you're doing the definite integral, resubstitute back at the end and then plug in your numbers, or you can change the numbers as we go, and that's what I'm doing. I plugged in pi over 3 right here. Tangent of pi over 3 is radical 3. And I plugged in 0. Tangent of 0 is 0. The integral of u is u squared over 2. Plug in your numbers, and we get 3/2. And one final problem here. What's going to be my u? I would let u be the x squared minus 4. Du is 2x dx. So I'll need a 2 up here. I'll need a 1/2 out here to offset it. Ready to take my integral. That becomes 1 over u du. The integral of 1 over u is natural log u. Now notice again, I changed my numbers. Negative 3, negative 4. How did I get them? I plugged 1 in for x, and I got negative 3. I plugged 0 in for x, and I got negative 4. Now we're ready to plug in. Don't forget the absolute. If you try this without the absolute values, it will not work. I'll plug in my negative 3 and my negative 4. It makes things positive. Both have a 1/2 out front, so I can combine these together. I'm using subtraction, so I'll combine them together with division. And that's all, ladies and gentlemen. Thank you very much.